Welcome today to the Colloquium. Thank you everybody for coming. It's my great pleasure to introduce our speaker, Professor Prineha Narang. She's coming to us from UCLA, where she's a professor. She started her studies at Drexel in material science and continued her graduate studies at Caltech, actually in an experimental group I learned, and went on to study theory. At that time, she was looking at quantum plasmonics and nitride materials for optoelectronics. Continued with a postdoc at MIT, where she was looking at computational models, developing these models for computing interactions, excited states, and non-equilibrium phenomena, a little bit more closely related to what you'll talk about today, I imagine. And started a faculty appointment at Harvard 2017 and launched a program based on light-matter interaction generally. Also started a quantum startup company, I think while you were in the Boston area, where you're currently chief technology officer. So that's something to keep an eye on. In 2022, moved to UCLA, where she's now a professor, and the Howard Rice Development Chair, so named professorship. So her new program is very cross-disciplinary. I think it involves condensed matter physics, but also chemistry, computational physics, many different fields, I guess, bringing them together. So that's a very interesting area to be in. She also serves as a science envoy in the United States, which is sort of at the intersection of science and policy. So it's a very important role that needs to be filled by scientists. So we thank you for doing that. And just to list a few of her many awards, she was Forbes 30 Under 30. She was also named a Young Global Leader by the World Economic Forum. CFAR, which is a Canadian organization, gave her the Azrieli Global Scholar designation, and she's also a recipient of the Millie Dresselhaus Prize. So without any further ado, I'd leave you the floor. Thank you.
Awesome. Thank you. Thank you so much for that introduction and having me here. It's really, really awesome to be here in person and have the opportunity to interact with colleagues all day and opportunity to now present my work to you. And as I gather, also get a chance to talk with some of the undergraduate students right after the colloquium. So I'm really excited to tell you about quantum matter that is driven out of equilibrium. And I'll try and convince you over the next 35 to 40 minutes that driving matter out of equilibrium actually gives us access to new properties, new functionality, and also brings up new questions in theory that require both new theoretical and computational methods. And as I'm going through this, I see there's a spectrum of people here today across fields. So if you have any question, particularly if I use a phrase that means something in a different area of physics, just raise your hand. I'd rather answer those questions as I go along and have everyone stay with me. So question that I get a lot is why non-equilibrium and why now, right? And the answer to that in part is because of the large number of sources and detection schemes that have become available to us. So the word non-equilibrium means something to different people across fields. Folks who are thinking about this in the context of atmospheric physics might be talking about non-equilibrium phenomena that are from a optics or condensed matter perspective very, very slow. So things that are out into the microseconds. There's a lot of work happening that is at the attosecond domain. And this is, of course, timely with the prize last year being awarded in attosecond science. And then there's pretty much many things in between that span different time ranges. So as you think about these time ranges and you realize, of course, you're looking at things across many orders of magnitude, I want you to realize that the types of sources, lasers, X-ray sources, free electron sources, ways of shaping these, ways of controllably exciting these phenomena have come a very long way, right? And that's in part why thinking about non-equilibrium phenomena today is so rewarding. So some of the work that I'll talk about today sits in this time domain. So I'm going to talk about things that are, say, tens and hundreds of femtoseconds, maybe going out to picoseconds. And when things head out to the nanosecond domain, that's usually when they start to, at least in our context, thermalize. And for us, at least from a condensed matter standpoint, stabilizing some of these non-equilibrium phenomena essentially means how do we go from something that is excited at that femtosecond, say, time scale and stabilize it. And if I get past this nanosecond, say, barrier, I call that victory, because from my perspective, that looks like steady state. Though for some of you, that might be the beginning of a non-equilibrium phenomenon. Okay. So and by the way, human perception sits all the way out here. So if you're thinking, are my senses a good measure of how non-equilibrium something is? Probably not, at least not in the context of condensed matter. From that standpoint, everything has thermalized. But almost everyone will tell you that in biophysics and certainly biology, it's all non-equilibrium, that life exists in non-equilibrium. So that is a genre of non-equilibrium that's past our time scale and probably not something that we'll touch on today. Okay? So from the standpoint of these ultrafast techniques, from the standpoint of the sources that have been developed, I want to draw your attention to how we will excite something, right? So you might think, okay, no problem. I have a giant laser. I'm going to shine it on matter, and there everything is out of equilibrium. Okay, we're going to do something a little more complicated than that, in that we'll pick the type of collective excitation we want to actually excite. So there are many options for types of collective excitations I can get in condensed matter, certainly in quantum condensed matter. The ones that will form the cast of characters in our story will typically be spin excitations in the form of magnons and lattice excitations in the form of phonons, okay? We're going to think about ways that we can very selectively probe the symmetry of condensed matter. Symmetry is a system that we're exciting. And we're going to also pay a little bit of attention to the element specificity that we have in some of these techniques so that we can look at phenomena that can be attributed to a particular type of orbital, a particular type of coupling, and not just everything that is possible in that material. Okay, and I'm being abstract at the moment. I'm going to show you examples of materials, but some of these themes will come up a fair bit, particularly this idea that we can actually use the lattice, phonons in particular, as both a probe and a way of selectively exciting other excitations in our material. Okay? So as we got into this field and started thinking about the types of sources, you might say it's all just about the time domain. Yes, but it's also about the spectral band that we can access, right? So where am I exciting? What excitation lives in what spectral band, and why am I picking that spectral band, right? So a lot of the magnons and phonons we are interested in live in the infrared and terahertz frequencies. Those are ones that are more readily accessible to us now, in part because of ways of generating terahertz, ways of generating, so the sources in those spectral bands have really improved. But I'll show you, in addition to work in the terahertz and mid-IR, that there are some ways of probing quantum matter in the microwave, particularly using the language of circuit QED, as well as ways of probing quantum matter in this X-ray domain that is also quite exciting. Okay, and if you're interested in this genre of physics, you're thinking, gee, I want to read about this some more. I encourage you to go look at this RMP from 2021. In the true tradition of RMP, it is long and extensive and covers a lot of ground, but perhaps that would be a good way to get started in the field. There are two things that immediately when you look at these types of excitations, this type of way of probing quantum matter, you might say, so you're just pumping in a bunch of energy into the system, right? So if you've thought that, how is this controlled? How is this creating new states? You're not the only one. In fact, turns out establishing that this is in fact non-equilibrium rather than just a thermal phenomena is half the battle. Okay, so what do I mean by that? Well, historically in the field of ultrafast dynamics, in the field of optics, what you would do is shine a laser on something, maybe you pick what type of quasi-particle you want to access. You'd excite it out of equilibrium, put it in some excited state. And then what you would really watch is the thermalization process associated with this returning back to equilibrium. And that would tell you both about the non-equilibrium properties as well as the equilibrium order parameter, right? What we're doing is fundamentally different. We are interested in non-thermal pathways that are triggered by optical excitation and creating transient states that then exist away from equilibrium rather than just watching the thermalization, okay? So that's one of the ways that this is actually different from the older ultrafast literature. And if you're used to thinking in terms of a potential energy surface, pick your favorite coordinate, a lattice coordinate, pick a nuclear coordinate, could be electronic coordinate, doesn't matter. If I'm probing the system, I'm usually sitting at the bottom of this trough and slightly exciting it, watching something happen. And I would say an equilibrium theory, perhaps something that is slightly perturbed from equilibrium, is sufficient to describe those types of interactions. Then we get to slightly more exciting scenarios where perhaps you have two degenerate ground states, switching between them, and you have a state that is slightly higher energy, but not too far away in energy. And you can access that easily. Perhaps there's some fluctuation that gives you access to that. Perhaps your drive is tuned just right to give you access to that. You could be looking at a critical phenomena or even looking at very strongly nonlinear phenomena, which is what I'm going to be talking about in a little bit, where we're using nonlinear phononics, not nonlinear photonics, but phononics to actually get some of these excitations to go, okay? And if you look at all of that and say, okay, well, fine, this is all going to eventually thermalize, you're right, it will eventually thermalize, but it will eventually thermalize on a timescale that we are not interested in, okay? So that's going to be the separation of timescales argument that I'll make, that where we're looking at and probing and creating this non-equilibrium state is different from the fundamental thermalization dynamics. Of course, scenarios where those two things start to overlap get more complicated, okay? Yes? Okay, so the question was, why am I looking at the potential energy surface to characterize whether or not we've thermalized? What I'm doing here is schematically showing scenarios where we might get out of equilibrium, but there's no thermalization that is shown in the top panels here. So I'm trying to make the argument that when we are looking at things that are fundamentally non-thermal, we're looking at something that's non-equilibrium, I ought to be talking about a distribution rather than talking about, say, an effective temperature. That's implicitly what I'm saying here. Excellent question. Okay, so as I have thought about this, of course, there are many results that started to come out, including this very provocative results. This is one on YBCO, a parent cuprate compound, where there was a claim that I can drive this cuprate, right? I can drive this system and therefore stabilize it above its superconducting transition temperature. Now, if you're listening to that, you're thinking, whoa, 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 what happened here? How that is so counterintuitive. It is counterintuitive because essentially I'm saying that there's some very, very pristine condensate, some very unique scenario where this forms a superconductor, and now I pump in a bunch of energy and I'm stabilizing it above its transition temperature, okay? But that's the kind of thing that is possible in non-equilibrium. This is not one of our results, but if you were about to zone out, hopefully this will keep you with me through the talk. So within my group, what we do is develop ways, theoretical and computational, of describing such systems. And we've developed approaches. I say that because one of the most frequent questions I get is, so what method are you using? And then there's this expectation. I have one acronym, maybe a couple of acronyms smushed together that I can give you, and that's the method I'm using. That is not the case, and I will try very hard not to throw out too many acronyms in this talk. What I will say is that there is a disparity in the types of methods that are available to us and their accuracy when it comes to both equilibrium and certainly when it comes to non-equilibrium phenomena. So on the left of this slide, there are approaches you'd recognize, say, or hear of in a quantum chemistry talk, in part because you have some notion of finite systemness here. right? So this is where I can perhaps explicitly work with the orbital. Perhaps I can talk about something that is very, very small, and I can get very accurate numbers out of those calculations, in particular associated with the energies, the splitting, perhaps thinking about the fine structure and quantities of that nature. But that doesn't look at all like one of the systems I just showed you, right? If you're looking at YBCO, you're thinking, this is a giant crystal. It's going to have everything happen in it. It has many components. It's got spin-orbit coupling. How are you going to take one of these approaches and apply it? And the answer is I'm not, because some of those approaches actually come from condensed matter, where I can talk about a notion of periodicity, and that allows me to downfold the problem a fair bit, allows me to talk about either at the mean field level about the behavior, perhaps then I can go beyond a mean field theory to talk about it away from equilibrium. So what we've done in the group is actually bring together some of these methods in weird ways, and that Frankenstein approach actually has some advantages. So, and those of you certainly who came to this talk thinking there's going to be a lot of quantum information science and wanted the CTO hat on, I'll say that for 30 seconds, which is that all of this is useful. In fact, if you ever wanted to design a type of quantum network or think about interesting new quantum sensing and quantum computing modalities, you ought to be looking at quantum materials for that. In fact, there's now a growing subfield of quantum materials for quantum technology. So you should enter this field. And if you're an undergraduate in the audience and that's one thing you're going to walk away with, please walk away with that. Okay. So how do we actually think about light interacting with matter? And how do I reconcile all of these things, these questions I want to answer from a theoretical standpoint? So first thing you might that might come to your mind is that light, and this is really a theorist view of the world, there's light on one axis, there's matter on another, going from very analytical to very computationally intensive techniques. You might look at this and say, fine, correlations between light and matter is something that we understand from quantum optics quite readily. This is something where I can treat the photon quite explicitly. I can treat the vacuum fluctuations. I can talk about that explicitly. You'd be right. Those are techniques that live down here. There's certainly phenomenal approaches that have come from the photonic crystal literature, ones where perhaps I can, if I know the epsilon or the chi, so I know something about the effective electromagnetic response, I can come up with transfer matrix type methods and say something about very, very large systems. Electronic structure, I think we've touched on that already. Something we've done in our group is actually both formally and computationally merge QED and electronic structure theory, going beyond approaches in non-equilibrium Green's functions. That's actually something that's been around for quite some time, and developed a whole hierarchy of these methods where you can actually have the photon and the electronic and the matter degrees of freedom there explicitly. This is relevant for two separate scenarios, okay? And this will be important for the next few minutes. There's a scenario where instead of directly driving the system, this giant laser scenario that I helped you into it over the last few minutes will be replaced by a cavity, essentially a scenario where the vacuum field is able to do all of the things that a drive is able to do. I haven't yet told you how we reconcile those two pictures, so take that as a given for a second. And the other scenario where this will be relevant is where I say that, hey, having the electronic structure there explicitly together with the nuclei actually allows me to think about temperature and non-thermal phenomena explicitly rather than artificially trying to build in some notion of temperature, okay? Yes? Absolutely. So these are finite element methods, and FDTD is one of the ways you could think about a finite element method. Transfer matrix, I think I talked about that. NEGF, non-equilibrium Green's functions. QEDFT, this is one of the ways that quantum electrodynamics and electronic structure theory are merged. Down here, I have GW, density function theory, and coupled cluster singles doubles. That's what CCSD, and then the T in there is just a level of that theory. So these are all acronyms that folks that work in these sub areas are typically used to, but I promised you that I wouldn't show you a smush of acronyms as what we use. And true to that statement, I'll say that we don't just take one of these, put it with another, and have some self-consistency loop and have that circle of happiness happening here. That is not what we have happening. In fact, the first thing we did in order to actually, and I promise I didn't prime him with that question, even though he's running the AP system. One of the things we did is to establish how an interacting physical system, which has electrons, nuclei, and photons, could be mapped onto an effective cone-sham system. This is a trick, sleight of hand, essentially, where we now have non-interacting nuclei, we have non-interacting electrons and photons, as long as I can find a good mean field exchange correlation kernel that actually captures this one-to-one correspondence. That's one of the ways that you could merge QED with electronic structure theory, something that we demonstrated you could do at the level of, say, the Hartree-Fock approximation, something you could do at the level of mean fields, but also do at the level of bringing in Green's functions and some of those other quantum chemistry techniques, okay? And the trick is always the same in that I establish this one-to-one correspondence mathematically in a general sense, and then I implement it for systems where I can find that kernel. That certainly works for anything that is going to be QED plus mean field theory. There are different ways I would do this for couple cluster and some of those other techniques. Let me not confuse the matter by talking about them. So as we go about doing this, it's important not only that we can formulate the problem, but also that we can computationally implement it. And that's something I'm not showing here, but you could take my word on it that we've been able to use both large-scale CPUs and GPU accelerated clusters to actually do such calculations for real systems. The real systems here means the types of complicated and in some cases annoyingly complicated scenarios I outlined previously. Okay, so stepping a little bit away from the equation, you'd say, fine, so you had the drive, perhaps the drive was modifying something like apparent recuperate, but then you kind of went the other route and said, I can also do it with QED and start talking about cavities, right? So let me show you one example where instead of directly driving or laser dressing, if that's the word you prefer, the superconductor, I could actually perhaps get to a similar objective by using a terahertz cavity. And now we're going to look at a terahertz cavity here, meaning something that can either be patterned directly, so not a Fabry-Perot. Fabry-Perot is the types of cavities where you kind of have the two mirrors. You talk about that. In this case, it might look more like a horseshoe, or it might look like one of these spirals or something like that. And we're going to be interested in polaritons meaning hybrid light matter excitations that exist in such systems. And the one we're going to look at are magnon polaritons, right? So for those of you who know where the story is going, fine, zone out for a second. But the objective will be that by controlling a polariton, by controlling, in this case, the magnons in something like a apparent Couperin, perhaps I could actually get direct access to the superconducting order parameter, get direct access to the condensate. This relies on a certain chain of thought that there's magnons. There are magnons in the system that are responsible for the pairing glue, something that folks in the Couperin literature have some strong feelings around. But if you can agree with that, then you could say that going via the magnons is actually a reasonable objective to actually modify the behavior of the condensate. Okay, so there's a cavity, and in terms of an energy level diagram, it looks as so. I have a spectrum of magnons that I can access. Now I'm going to look at, once again, YBCO. For those of you who've seen this diagram before, yes, it's C-axis. In fact, the C-axis IR active phonon is going to be very relevant in our story here. This is a phonon that you could either pump directly, you could directly optically excite it, or you could couple to it via a cavity. And the other component of the story will be that I have several magnons that can either couple to this phonon, or I have these magnons that can directly couple to the cavity, right? And the story goes as follows. I now have an ability via the phonon polariton to control the condensate, or I have the ability directly via the magnon polariton to control the condensate. And that's a way for us to get access optically to this superconductor. so far, and I want to distinguish this from what the aspiration was, what we've shown is that yes, you can couple to the magnons, both the single and the bimagnon operator in this case. You could also go via the phonon, and that does give you some control over the magnon polartons in the system. What we haven't yet established is that this allows you to now do something that you wouldn't expect with the superconductor, okay? So I just want to kind of distinguish those, and this is now become its own little area and work that was done by postdoc who worked with us on this topic, John Curtis, and graduate student Nick Poniatowski. What they've been able to establish is that directly using the cavity to couple to the superconductor maybe is ambitious. That's something that John had shown in his prior work, but going via the magnon polarton is in fact a viable route. So all of this led us to think that, you know, the phonon is the important ingredient in this story. Remember, I said our cast of characters will be magnons or phonons. And what we start to agree on is that going via the phonon has a lot of advantages, whether it's a cavity or the drive. All it is the right shaky, essentially, right? Okay, so you can do a little like shaky dance. So with that, and this has some history from the literature in ultrafast spintronics, where you can talk about either linearly or circularly polarized light, drive, go from antiferromagnetic to a ferro or ferrimagnetic state. And that's been around for a while. Two things to remember, that the timescales that we look at for something that controlling a ferromagnet versus an antiferromagnet are different. So one of the things that you really need to be ultra fast for is for the antiferromagnetic case. But fine, no problem. In this case, we and others have shown that you can do a lot just by driving these between various states. So what's the right shaky though? Right? What's the point of the right shaky? Well, this idea of phonon-driven superconductivity, we've touched on that. You could have phonon-driven ferroelectricity. You could directly dress these magnetic or these vibrational excitations that you could magnetically dress them in the sense you drive the magnon that then couples to the phonon. So the whole thing kind of is in this coupled scenario. Or you could do some kind of topological symmetry breaking. All of that essentially gives us the same outcome, that we have access via the non-equilibrium drive to the order parameter. So next, maybe a couple of minutes, I want to tell you why and how we go via the phonon. And I had a couple of discussions earlier today about this, so I want to spend a bit of time on this. So when you start thinking about light interacting with something that's magnetic, first thing that comes to your mind is there's optomagnetism and magneto-optic effects. These have been known for some time. The Faraday effect, for example, I'd argue is very well established, as is the inverse Faraday effect, the Cotton-Mitten effect, and the inverse Cotton-Mitten effect. And the inverse here basically means whether it's an optomagnetic or magneto-optic effect, right? Very similar to talking about things in electro-optics for those of you who are familiar with that. So no problem. I can go with whatever polarization, circular or linear, and talk about this coupling. Alternatively, what I can do is go via the phonon. And that's important because and I intend to say the word phonon here, not photon. I'm not misspeaking, not undercaffeinated, because instead of driving the magnons directly, I can now talk about the phonon that gives an inverse or phonon inverse Faraday effect or a phonon inverse Cotton-Mitten effect, okay? And like everything in condensed matter, just because I can write down an effect does not mean it will exist, certainly doesn't mean that it will be a dominant contributor. So something we've established over the last few years is that both to first order, the phonon inverse, and to a second order in the magnetization, the phonon inverse Cotton-Mitten, in fact, both exist and can be larger than their traditional magneto-optic scenarios, okay? We established this, and this is work by one of my former postdocs, Dominic Yershek. Dominic is now a junior faculty member at Tel Aviv University. So what we're really doing is calculating the susceptibility in the inverse Faraday, the susceptibility. We're interested in dynamical matrix in the context of phonon inverse Faraday effect. But in both scenarios, we have two the same order, an optomagnetic effect versus, or field, I'm sorry, and a photomagnetic field. These are effective magnetic fields, synthetic fields, whatever phrase you want to use, particularly if you come from an AMO context, you might prefer synthetic fields. It's the same scenario, but in this case, we have this QQ star type coupling related via the dynamical matrix, okay? We looked at this in a particularly exciting scenario of a rare earth trihalide. And I got a chance to do something I wanted to ever since I entered the field, which is use the word giant in the title of our paper. So we call this the giant phonomagnetic fields in cerium trichloride, but actually there's a whole bunch of these where you can get effective magnetic fields that are very, very large. And I'm going to run out of time, so I just want to show you one of the results here, which is that for cerium trichloride, there are two phonons you could equivalently drive that are both E1U modes, a 4.8 and a 5.9 terahertz mode. And they're essentially opposite chiralities. And what you realize is that by driving one of these chiralities, you can get really a very, very large field. In this case, an effective magnetic field that is nearly 100 Tesla. Again, effective magnetic fields have fluences that are very, very forgiving. We made this prediction, and initially folks said, sure, this exists, but really most people are going to be melting the crystal. This was just independently verified in a paper that appeared in Science for this same family of rare earth trihalides. And we were able to relate this nature of this 4F paramagnetic spin, its response to what's happening, okay? And this, by the way, leads to a whole set of generalized approaches to such magnetic control. Dominic and I have written about it, and I believe some of you here in the audience or undergrads should have gotten this as pre-reading for our discussion after. So it doesn't have to be a single phonon, single magnon, right? We know this from nonlinear optics. Once you have one, you can nonlinearly have more. So you can have some frequency or difference frequency type processes. You could have up conversion, down conversion, 3-wave, 4-wave mixing. And it turns out everything you've seen in a nonlinear optics textbook, perhaps something you've seen in Professor Sipe's course, can be possible with magnons. And in a series of papers that just appeared a few weeks ago, I won't have a chance to touch on them. In Nature Physics, we report what this nonlinear magnonics looks like and what 3-wave mixing in these situations looks like. So if you haven't read those, please read what we put out and tell us all the ways this will not work in future, even though we do have a lot of experiment in there. Okay, so I haven't so far established, besides showing you that, yes, this is all possible, equations exist, the traces should look similar. I haven't established yet that this is, in fact, non-equilibrium, right? Everything so far could conceivably be explained with an equilibrium theory, could be captured and talked about as an equilibrium phenomena. So for the next few minutes, I want to show you results that are in this system YTO, where we show conclusively that this is actually something that's non-equilibrium. And what we're going to look at in YTO is a system that sits on the ferro and antiferromagnetic boundary. So this is a system that can very readily pick one or the other ordering. And it undergoes, as it picks that ordering, a gadolinium ferrite type distortion. Okay, it has orbitals, it has spin-orbit coupling, it has all kinds of things that can happen. And our claim that will make this non-equilibrium will be as follows. Okay, the claim will be that by driving the system, either I pick the ferro or the antiferromagnetic order, and I stabilize this behavior above its transition temperature. That same claim we made about superconductors, we're going to make it a little bit easier to palette and make that in the context of stabilizing this ferromagnetic response. Okay, we're going to probe this using time-resolved magneto-optic Kerr effect. This is going to work for a few reasons. So I'm going to come in with a mid-IR excitation, pump very specific phonon modes. This is not something where I'm increasing the thermal population, because remember, I'm trying to establish this is a non-thermal, non-equilibrium effect, right? So I'm going to resonantly drive them, pick modes that have strong coupling to the spins. It's going to be all about that spin-phonon coupling. And then we're going to probe the time-dependent magnetization via this magneto-optic Kerr effect, okay? And this is going to be at different temperatures, fluences, all of that. So those of you who are laser jocks in the audience can go look at that and say, yes, everything was established, nothing melted, nothing reconstructed. We actually did the measurement that we're talking about, okay? The 3 phonons that I'm going to be most interested in is a 4, a 9, and a 16 terahertz mode. Out of this spectrum and set of options, these are all B2U modes, I picked the ones that have a large magnetic field dependence, but also ones where I have this selectivity. So what am I talking about with this selectivity, right? So we're now looking at the Moch angle. Essentially, this time-dependent magnetization is going to show up in terms of a rotation. So you can think of a certain rotation corresponding to stabilizing that ferromagnetic order and the opposite rotation corresponding to stabilizing the opposite order, okay? If you do Moch measurements, this is definitely a simplification of what's going on, but it's a simplification we have to live with right now. So the 4 terahertz mode, it seems like goes in the opposite direction here, right? Whereas the 16 and the 9 terahertz mode are both positive Moch angle. What we're really doing, and let's just look at the most prominent response here, which is this 9 terahertz mode, where we're essentially stabilizing the system above its transition temperature. So you might ask, what is the equilibrium transition temperature? The equilibrium transition temperature for this system is about 27 Kelvin. This has been reported endlessly. In fact, the first report of this being the transition temperature in the system, it was before I was born. So this is something people can agree on. And what we're doing by pumping this 9 terahertz mode is actually stabilizing it all the way up to, say, 80 Kelvin, okay? So that's not something that is in the noise, not a slight shift to TC, but definitely a serious modification. So showing that we have this optical stabilization of this above its transition temperature is not the same as understanding everything associated with the timescales. So we have a tale of 2 timescales here. The rise is very fast, and the decay is very slow. If you're paying attention to this time axis, you realize, wow, this goes out for hundreds of picoseconds. If you remember from a few minutes ago, the cerium trichloride story was about tens of picoseconds, right? So it looks like once you excite the system, it stays there. And typically when you see something like that, you say there's some bottleneck. It just can't relax. It's stuck, right? So yes, there is an angular momentum bottleneck. And that's in part because of this interplay of spin-orbit coupling as well as orbitals. But that's not the full story. The full story also involves the fact that the system, despite the drive being turned off, actually feels like it's in this driven state, almost feels like it's remains out of equilibrium. And this phonon ring down is in fact commensurate to that rise time if you think about it. So during the ring down, which is what you would expect, so you'd expect a super fast rise and then a ring down that looks like that, it stays in that quasi-driven kind of scenario because the system effectively feels driven even after the drive goes away. And this is work, again, due to John Curtis. And I forgot to mention, but the measurements, the Moch response here was all work done by Ankit Disa. Ankit is a faculty member at Cornell now, in collaboration, of course, with the group of Andrea Cavallari. You can look at these results appeared last year, both in Nature and in PhysRev. You can go read about them. So after all of that, and understanding kind of these timescales, the fast rise, the sidebands, the spin-orbit coupling, we spent a lot of time establishing the non-equilibriumness of this. And this became one of the first kind of reports of, I would say, reports of such orbital stabilization. Okay. I alluded to this. We've looked at this in the context of upconversion. Won't really have time to touch on it because I want to spend the next maybe few minutes talking about time reversal symmetry breaking and talking about how and why this is actually so hard to do, right? Yes. Okay, so the question was, what changed when we were stabilizing, right? So we stabilized the ferromagnetic order with that 9 terahertz mode, and showing it, showing our preferential creation of the antiferromagnetic was the 4 terahertz kind of the response going in the opposite direction part. So the 16 and the 9, both the positive Moch angle, were related to stabilizing the ferromagnetic order, and the 9 terahertz mode is the one that you get the big response from. the big change from equilibrium TC to 80 Kelvin. Yeah. Okay. So far, yes. Got it. Yeah. So we've talked about magnetic systems and scenarios where time reversal symmetry is naturally broken, right? So a question that comes up a lot in condensed matter is, and this is broadly across condensed matter, types of condensed matter, is how do I characterize time reversal symmetry breaking? And this shows up in the context of types of two-component superconductors where you might have time reversal symmetry breaking. This shows up in the context of spin liquids. This shows up in various contexts, right? And what we, and certainly this is folks in our group as well as in the group of Amir and Kobe, what we started thinking about is, is there a more general way that we can actually characterize time reversal symmetry breaking where we're not all constantly arguing how much of the technique is related to what is being measured, right? And there's a lot of ways of going about this, but I'll just say that thinking about time reversal symmetry breaking is relevant. Characterizing non-abelian anyons, if you really want to get controversial, that's a route you could go. You could think about, types of topological superconductivity, spin liquids. So essentially, we concluded that ways to detect unconventional pairing, right? And those of you who come from a superconductivity literature will say, yeah, everything that isn't the simple kind of S-wave gets kind of put in this category of unconventional pairing, but I'm talking about scenarios where there's actually explicitly time reversal symmetry that's violated. How do we actually detect that in kind of mesoscale scenarios, okay? So one way would be for us to already know something about the current response in the system, right? And do, say, some kind of magnetometry, right? And here, the argument would be that magnetic fluctuations have some valuable information, and I can reconstruct from there what's happening. That's the whole point of NV magnetometry. And that's been reported. We and others have done that for particular scenarios. It need not just be NV magnetometry with a classical picture in mind. You could actually think of it as essentially noise magnetometry as well. Get very, very good resolution. Think about layered materials, 2D materials, get very close to the surface, reconstruct what's happening, maybe reconstruct the current profiles. It does a little more than a typical transport measurement. And I know there are a lot of prominent transport experts in the background. The claim here is not that this replaces a transport measurement, but that it adds to a transport measurement in allowing you to understand some of these layered systems, okay? But if you want to take that a step further and think about really generalizing, and not trying to do magnetometry, not being reliant on knowledge of the sample. This is kind of, in some ways, the holy grail. So your favorite friend synthesizes a spin liquid and gives you a sample at breakfast. How do you tell them by dinner time whether or not they have something that has broken time reversal symmetry, right? That would be kind of the happy scenario. And I put that time frame on there because, you can't go do mu-SR. You can't go do a fancy Kerr rotation measurement. You need to know by dinner when you see this friend what type of sample you had, right? To do that, we're going to use the idea of using circuit QED to probe quantum matter, okay? I'll say this with kind of some generality that thinking about circuit QED and this language of LC circuits, so thinking about inductors and capacitors, I can show that this is going to be exactly analogous to the cavity picture, the Fabry-Perot cavity picture, or the more quantum electrodynamical picture I had previously. And I can also show that this can be kind of more generally thought of as doing some version of quantum sensing of quantum matter, okay? Essentially, it's using circuitry that is common in superconducting realizations. This is essentially a crude version of what IBM now uses in order to actually make their superconducting quantum computers. But instead of making a quantum computer here, if you really wanted to do crappy fab, you would still have a great sensor. You would arguably have a way better sensor than you could ever make by doing very pristine fab with something that is purely classical, okay? So what I'm going to do now, I have this LC circuit. I'm just going to pop in this quantum matter sample that somebody gave me that day. And the hope is that I can, by leveraging the high Q and the long coherence of such circuits, and seeing the coupling of this quantum matter to this classical LC circuit, know something about my system. Really, what I'm saying is that the quantum capacitance here is related and directly relatable to the many body density of states, and that the quantum inductance can be related directly to the superfluid density. Okay, the superfluid density component, essentially here, thinking about that with the kinetic inductance, basically means that if I have nodes, I don't have nodes, what types of pairing I have should immediately show up in measurements of that quantum inductance. So with that knowledge, the hope is that I'm sensitive to the nature of the gap. Perhaps if I go back to my continued story of YBCO, again, by looking at the types of superfluid density I have, I should be able to say whether if this is a nodal or not superconductor. And then we get into questions of how would I distinguish something that is, say if somebody had synthesized P plus IP, or if I had something where the pairing interaction is not known at all, perhaps a twisted bilayer type scenario, what would that look like? So as we went about doing this, we realized that we were actually sitting on something that was an even more general technique. Even though we started down this route of time reversal symmetry breaking, we realized this is a general way of understanding non-reciprocity and ways of understanding symmetry, time reversal symmetry breaking. And the same ideas that I have from transmons, from circuit QED, instead of just a single resonator, which is what you typically use when you're making a qubit, I could have a cross resonator. By the way, I could design these resonators however I see fit. And then I could essentially do quantum metrology on quantum matter sitting in this cross resonator, okay? So I could figure out how I want to occupy these. And then everything that I think about in quantum sensing or quantum metrology, I can do here, including state tomography, optimal control, all of that essentially becomes available. And this is insight that was led by Yannis Vitridis. By the way, Yannis is on the job market. So those of you who might be contemplating that, please contemplate his application. And the experimental realization is being led by Marie. This is something that we recently filed IP on, as well as this should appear soon. So in this scenario, essentially, I don't need to know pretty much anything about the system, because what I can do is first tell you and classify it as reciprocal versus non-reciprocal. And then going that non-reciprocity route, by doing some of this tomography, I can tell you, does it really break time reversal symmetry in its in condensed phase or condensed state? And then what, is it single component, two component, is there a relative phase? Or if I want to think about spin liquids, I can then start to relate the information I extract from tomography of such a system directly to the quantum Fisher information, okay? So many jumps there. I trying to cram in as much as I can in the last minute or so that I have here. But then, it all becomes a matter of designing just the right resonator, figuring out what that resonator can access, whether I'm able to use the coupled angular momentum states to actually disentangle types of symmetry classes. That's going to be relevant. I'm looking at topological superconductors, and the story goes on from there. I won't have a time to talk about the ideas we now have, and also collective excitations in triplet superconductors. But if you have questions around that, I encourage you to ask during the after hour part of this. So I want to leave you with just a quick thought, which is that, and maybe there are some high energy physics folks here in the audience who come to a condensed matter talk. If you're here, thank you for being here. I'll say that, in condensed matter, we've learned a lot from high energy. We've taken some of these ideas from, say Higgs and types of Higgs modes you can excite, and in characterizing superconductors, that's become a whole field of Higgs mode spectroscopy. Of course, very senior condensed matter folks will say it's the Anderson-Higgs mechanism. Sure, but I think we've found some good ways of learning from high energy. Certainly done that for Dirac and Weil semimetals. Something we've been asking now in the group is, can we do something similar with knowing something about axions and knowing something about axion electrodynamics? And if we can get really fancy, perhaps we can give back to high energy by taking some of these insights and mapping them back to ideas in HEP. So that's something we've more recently been doing in the group. Won't really have time to talk about this, but just to kind of leave you with ideas here that, even starting with something as simple as, say, a Dirac semi-metal like graphene, folks have made a lot of progress, Floquet driving it, understanding things about the chiral anomaly, certainly in the context of valence semi-metals. Now, of course, understanding axion insulators. And a question is, what new topologies, what new phenomena can we find? I've shown you maybe some ideas around this, that cavity control can get us there, driving it optically can get us there. Perhaps we can think about these types of quantum metrology, quantum sensing schemes to understand the types of symmetries we've created or broken. So if you're entering the field, now is a great time, because I think many, many more things are possible today than they ever were. With that, thank you for your attention. Happy to take questions.